similar to the lecture that Parikshit gave.
Right.
We'll look for the difference.
Okay. Okay, so I'm going to talk about pseudorandom generators for certain class of circuits. And so let me start off with some basic definitions, though not too much of it should be new to this audience. So just to fix some notation, so an epsilon pseudorandom generator epsilon PRG for short. So for a class of functions, so let me say the class of functions is f, and all my functions will take as input, what do I want? Let me think of my functions as mapping -1, 1 to the n to -1, 1. Right. So some class of functions mapping n bits to 1 bit is essentially a function that produces a distribution that looks uniform to this class of functions. So what does that mean? So that for all this class of functions, so standard definition. Equivalently, I could also say the two definitions might be off by a factor of 2 or something. Right. So this is what it means to be a pseudorandom generator for a class of functions. Right. And what we are going to be talking about are pseudorandom generators for classes of circuits. And in general, this is a fairly hard problem. So why is that? So here's a folklore fact: pseudorandom generators for circuit classes, well, they are at least as strong as circuit lower bounds. So they yield Boolean functions that cannot not just be computed, but cannot be computed even the average case. Okay. So this is why this is a fairly hard problem. But it does make sense to ask for pseudorandom generators for class of circuits where we do have lower bounds. Right. So let me just survey some of the results that motivate our work. Right. So classically, some of the first circuit classes that were looked at, one of the first circuit classes looked at was the class AC0. Right. So what is this class? This is the class of functions computed by polynomial size, constant depth circuits made up of using AND or NOT gates. Okay. And so we've studied this class of circuits for a long time, and so we have fairly strong lower bounds for this class of circuits. So building on work of first Sachs-Sipser, Oitoy, Yao, and finally the work of Hostad, we know that the parity function cannot be computed by AC0 circuits. So I'm going to abuse notation here. AC0 circuits of size write it a little bigger. Right. And depth d. So we know this, and we even know this on average. So what does that mean? If I take any circuit of this size, then let me call that circuit C. The probability that C equals parity on a random input, well, this is not very much larger than half. More or less. Okay. Oh, this no. There should be an omega here as well. Yeah, the double exponent is d minus 1, right? From Haus, but that only follows from Hausdall's proof, right? Yeah.
D minus 1 is in parentheses.
Yeah. As in. Oh. Oh, right. Good. Okay, I see what you mean. Okay, yeah. So good. Right. So using these strong average case lower bounds, Nissan gave the first pseudorandom generators for AC0. So right, but before I even get there, so I should mention that for all circuit classes we look at, we do know that pseudorandom generators exist. So we know non-explicitly that there exist PRGs with seed length. So if I'm looking for pseudorandom generators for circuits of size S, there are PRGs with seed length log S plus log 1 over epsilon. Okay, so this is always the ultimate goal that we are going to be shooting for. So using these average case lower bounds, Nissan was able to make progress towards this goal for AC0. So this was I think 88. So Nissan gave pseudorandom generators explicit.
I have a question about, so the PRGs for circuit classes imply the average case circuit lower bounds?
Yeah.
So non-explicit PRGs do not imply anything?
Oh, they imply non-explicit lower bounds, but that we know anyway,
Okay.
because a random function is very hard.
Okay, yep.
Right. So explicit PRGs, epsilon PRGs with seed length, well, not quite the optimal thing that we'd hope for, but something like log S over epsilon to the order d. Polylog. Okay. So I think in Nissan's proof it's 12, but
And so
maybe.
for the non-explicit, where does the D show up in?
It doesn't show up, it just depends on the size.
Right. So yeah, right. So that just holds for arbitrary Boolean circuits of size S.
Just the number of circuits of this
I
size
see.
for the counting argument.
Right. Yeah. So right. So this as far as I know, was the first paper to use the NW paradigm. Right. I mean the designs.
Well,
And
started,
right. Right. Good. So right. So right. So from these results onwards, we know that strong average case lower bounds for certain circuit classes can also be used to build pseudorandom generators. So okay. So right. So this is one of the first circuit classes that was looked at, and to a certain extent, the program of converting circuit lower bounds to pseudorandom generators was successful for this class. So, but our attention today is more or less focused on a related and slightly stronger circuit class, which is AC0, but with the added power of parity gates. Okay, so I know that parity cannot be computed by AC0, but what if I augment AC0 with the power of parity gates? So now they can take parities of input bits, of intermediate stages of computation, and so on. Right. So this is again poly size, constant depth. I allow and or parity not. Right. And so it's kind of easy to see that, and I'll use the fact that a general AC0 parity circuit only needs AND parity and not gates. You don't really need OR, right? By De Morgan's or something, you can always get rid of the OR and write in terms of the ANDs. So I'll just get rid of the OR. So just AND parity and not gates. Okay. So okay. So again, so this was a natural circuit class to study after AC0, and we have lower bounds for this class as well. So Razborov in something like 87 showed that the majority function requires circuits, well, AC0 parity circuits of size 2 to the n to the in depth d. So if you're trying to compute majority in depth d using such circuits, you really need exponential size, and d is constant. Okay.
Here d minus 1.
Here, yeah, I don't think we know d minus 1.
But it
Could be d minus 1. So then, yeah.
is the upper bound equal to C2?
The upper bound for majority with d minus 1. So you can do it in AC0 with depth roughly d and this size. Okay. So right, but here's the catch about this lower bound. This thing does not yield average case lower bounds. Right here, here. So so let me be more precise. We cannot make statements of this form. We can make statements of this form where we replace this factor by something that's inverse polynomial. Right. Well, it depends on whether you go to exponential size or not. Right, sure, but right, but 1 over root n is not even true for exponentials.
Yeah, that's the limit of the method.
That's true. Right.
So 1 over root n is even for polynomial size.
Well, look,
I mean, you can get 1 over root n bias,
Yeah.
right? Just by spitting out
Exactly.
one bit.
Right, exactly. So, and in general, if you are allowed size s, you can do something like half plus polylog s over root n.
Because you can just compute it explicitly on that and use that. On some,
Right, right, exactly.
okay, so it's not. I mean, it's not a limitation of the method. It's a limitation of what's true.
Exactly.
No, it's a limit.
Yeah, so
majority function.
Right.
Yeah.
For
Okay,
most
fair
three, probably the bias is exponential.
Right.
It's
Right.
For majority, that it doesn't work.
What if you try doing like a parity of a small number of majorities or something? Or I mean.
So the thing is,
Question how to program it.
yeah,
Yeah,
so
no, but I mean, would you expect some?
it's possible, but the standard proofs of things like XOR lemmas and things of that nature, we can't really carry out in the context of AC0 with parity gate. So standard kind of hardness amplification techniques don't go through in this setting.
Because they require majority.
Because they require majority, right? Right. So as a result, well, we don't really expect pseudorandom generators using this technique for this circuit class, and indeed we don't really have any pseudorandom generators that match these kinds of parameters. So let me tell you the best pseudorandom generators that we do have.
What did Smolensky get for?
Okay. So
He got the same for any mod B. He got the same result. He was able to generalize Razborov to any mod B, and not
Right.
just against majority, but against any mod B. At the same time. The one of the same.
right.
What's the cap?
Mod 3.
Mod 3 for exponential.
Yeah. You can make it biased. Yeah.
Right. Okay. So so the best pseudorandom generators we have for this general circuit class has very poor stretch. So the best result that I know of is a recent result of Pfefferman, Schaltiel, Umans, and Viola, and this achieves a seed length of n minus n over polylog n. Okay, so the stretch is really sublinear here. We don't even have some like 1 minus epsilon times n. Okay. So it makes sense to study kind of restricted classes of this general circular class, right? Yeah. So given the poor kind of results that we have for this class in general, it makes sense to look at restricted cases and see what we can do there. And it turns out that that's been done in many cases. So let me describe a few cases to you which are of interest to us. So one easy way to kind of restrict this class is by depth, right? So this is arbitrary constant depth. What about depth 1, depth 2? So it turns out that depth 1 is very relevant to what we're going to be doing today. So let's just look at that. So depth 1 is more or less just a parity gate. Right? So you have a single parity gate of maybe a subset of your variables. Okay, so that's more or less depth 1. You can also allow an AND gate, but really parity gate is the hardest. Okay. So we do have very good pseudorandom generators that fool these tests. So these are called small bias spaces. Or in general, if I'm talking about an epsilon PRG, these are called epsilon bias spaces. And these were constructed by, well, first by Naur and Naur in somewhere around 90, and then also by, so Alon, Goldreich, Hostad, Peralta, something like 92, gave 3 more constructions of these things, and all of these achieved the optimal seed length, exactly what you would expect, up to constant factors. Okay. So when we restrict the depth to 1, the question is completely resolved. And more generally, so if you think of parity gates as just being linear polynomials over degree 1 polynomials over f2, we also have the answer for degree d polynomials. And this is more recent work. So starting with the work of Bogdanov and Viola, then Shachar, and finally a work of Viola. We have pseudorandom generators for degree d polynomials with seed length something like well, this is what we'd expect, but we also have this.
So how are you considering depth 1 as degree 1?
Oh, so depth 1 is just a parity gate. So it's just a parity of a subset of your input variables. So that's like you're summing up a subset of your variables over f2, right? Right, it's an f2 polynomial. Yeah, all this is over f2. When I'm talking about degree, this is over f2. Okay. Right. So yeah. So the nice thing about this is that for all constant degrees, this is optimal. The not so nice thing about this is that the dependence on degree is really bad. In particular, when the degree approaches log n, you really get nothing. Okay. Yeah. Okay. So the direction we take in this work is kind of orthogonal to these things. So we restrict ourselves to very special kinds of circuits, read once circuits. So I really shouldn't call them circuits, they are really formulas, read once formulas. Okay. So here the circuit is restricted to a tree. Okay. So the fan out of every node is 1, and every variable appears at most once. So it turns out that read once formulas have been looked at in slightly different scenarios. So there's a recent work of Bogdanov Papa Constantinu, and 1 that looks at read once formulas with no restriction on depth, but where you allowed just AND and OR gates. Right. They look at constructing pseudorandom generators for this class of formulas, and what they are able to do is, well, they are able to achieve something slightly better than what we know for AC0 with parity gates in general. So they are able to achieve something like seed length 1 minus epsilon times n, where epsilon is some non-zero constant. Maybe 0.1. So no, so there I'm talking about circuits of size n, right? So sorry, I should have written this in terms of, yeah. So good. Let me just make that. Right. Maybe it even works for polynomial size circuits. I'm not really sure actually. So definitely it works for circuits of size n. Maybe it works for polynomial size circuits. I'm not sure. Yeah, it does work for polynomial sizes. Right, for read ones there's no distinction, right. Okay, good. So what we're going to do is look at read ones formulas, but in the setting of AC0 with parity gates, and I'm sorry?
No, but anyway, it's not with one. No, it's not with one. No, it is with one, but it turns out it's not again.
Right. So okay, yeah, so
And mean David and Russell have this thing where you can get square root.
right, right. So yeah, so that, but that implies, yeah, that applies to arbitrary gates and arbitrary depth, right. So okay, so I should probably just mention that result. So this is okay, okay.
It's a secret.
You don't want
Right.
it to be on the board. Maybe
Okay, so yeah. So and this is for, again, this is formulas, read once formulas, arbitrary gates, arbitrary depth, but so seed length square root n.
Change your name to reverse the role.
Yeah. Okay. So so in this in our work, what we do is we essentially achieve the parameters that Nissan achieves for AC0, but in this very restrictive read once setting. So this is just for AC0 parity read once, and the seed length we get is something like
Actually, over and or gates, we can get something better against the 2.
I see. Okay. Okay. So is the result clear?
Do you get anything for constant read?
Right. So constant read is no, as of now, no.
It works for other moduli.
Right. So good. It turns out that what I'm talking about will also apply for AC0 with computation, not just mod 2, but mod any constant number, prime or composite. So let me just define what that means. So in general, if m is some natural number, a mod m gate for us, some, let's say G is a mod m gate if G of x1 through xn is, say, 1 if and 0 otherwise, where these alpha 1 through alpha n can be some constants in the ring Zm, and A can be an arbitrary subset of Zm. Right? So you are allowed to do some sort of computation mod M, take some linear combination of your inputs mod M, and accept if this linear combination lies in some set. It seems fairly general. And so it turns out that whatever I am going to say also applies. So a result also applies to this setting. So AC0 with mod M gates. Yeah. But there is some dependence on M in the seed length. So the seed length may be something like whatever I said earlier. Times some poly factors on M, depending on M. So maybe M to the order D, I think.
These hold even if D is slightly super.
Right. So everything goes through for D up to square root log n. So there's also a 2 to the D square factor sitting here that I haven't written down. So everything works until then. Okay, so now let me start with essentially the proofs of our results. It turns out that the proofs are fairly elementary, and they kind of hark back to older results and older constructions of epsilon bias spaces due to Naur and results of Avi and Aitai on AC0. Okay, so here's a basic roadmap for the rest of the talk. So what I'm going to do is I'm going to start off with the first kind of non-trivial case of our result, which is the depth 2 case. Yeah, and hopefully I'll do this in detail because it's fairly easy. And oh, okay. So I'll start off with the depth 2 case, and so hopefully I'll do this case in all its detail. The arbitrary depth case is more of the same, but there are some sort of technicalities that need to be handled. And throughout I'm going to assume that M equals 2, so I'll avoid the complication of arbitrary moduli. That just introduces a few more technical complications, and there's not really all that much that's new there. There is a big difference as far as general techniques are known, but not as far as our techniques are concerned. So our techniques carry over more or less as usual. Sure, but yeah, right. But for read one circuits, lower bounds are not really an issue at all. So right, our techniques kind of completely bypass that. So it's somewhat orthogonal to that issue altogether. Right. So you'll see that whatever I say is not really going to be very specific to parity. So AC0 read one's AC0 parity is probably not even complete. Yeah. Right? I mean it's yeah. So right. So just take, I don't know, S4 or S2 even, the symmetric polynomial of degree 2 over F2. That cannot be computed by a read one's AC0 parity circuit. Oh, an average? On average you can easily prove a lower bound for mod 3 if you want, but I don't know if you can prove it for this particular. It will be 2 to the minus omega. Okay. Right. So the depth 2 case. Okay. So
so the relationship between PRGs and lower bounds doesn't hold in the read one set, right?
The relation in which direction? So PRGs imply lower bounds always, but the converse direction, the NW thing doesn't go through because yeah, the read one's character of the circuit changes. Yeah. It's no longer read one circuit. Okay. Right. So depth 2 case. So what I'm going to do is I'm going to start off with more essential. So with a candidate PRG, we are going to first see that this candidate PRG doesn't work, and this is going to motivate the actual construction. Okay. So it turns out that what the class we are looking at, AC0 with parity gates, Well, it's a hybrid of two classes. It's you start with AC0 and you're adding parity gates. So the natural thing is to start with a pseudorandom generator that fools both these classes and see if it fools this entire class, right? And we do have pseudorandom generators that fool both these classes. It turns out that the small bias spaces that I spoke about, small bias spaces with seed length log n to the order, well, it's not quite order d, it's order d square, log n over epsilon to the order d square, fool both AC0 and parity gates. Right. So, this uses a result that I haven't talked about so far that I forgot to mention. So, small bias spaces are by definition things that fool parity gates. So, of course, they fool parity gates. It turns out they also fool AC0, and this follows by a result of Braverman, who shows that polylog-wise independence fools AC0, and these things give you polylog-wise independence. So, almost. Right. Okay. So, as a result, these fool both AC0 and parity gates, and the most natural question to ask, therefore, is well, do small bias spaces say fool depth 2 read once AC0, say. Yeah. It turns out the answer to this question is no. So why is that? Well, here's a counter example. So define the following read once function, the inner product function. So this is going to be a function that maps, looking at the -1, 1, maps 2n bits to 1 bit. So I'll think of this function as taking two n-bit inputs x and y, and outputting the pair. I mean, outputting the inner product of the two mod 2. So here are a couple of simple facts about this function that's easy to check. So the first thing is that inner product is balanced, very, very close to balanced, in the sense that the probability that the inner product function takes value 1 is very close to half on a random input. But on the other hand, the uniform distribution over just the zeros of this function is a very good small bias space, is an epsilon bias space for epsilon equals, so this, okay, so here's a very good epsilon bias distribution, but at all points in the support of this distribution, inner product always takes value 0, despite the fact that it's balanced overall. Right? So clearly epsilon bias spaces do not fool the inner product function in particular, but in general depth 2 read once CC 0, because this is depth 2. So this in general yields a large family of counter examples to.
It's not going to work if you take the previous one.
So what's not going to work? Sorry.
This counter example, if you took. So this is for every, if you wanted every epsilon bias.
Sure, right. So I cannot say that blanket. I cannot make a blanket statement of the form that epsilon bias spaces fool depth 2 read once CC 0. This does not rule out like specific examples, absolutely, right? And of course it cannot, because a random set is an epsilon bias space and also fools this. So.
No, but even specific ones like
right.
quadratic character.
Oh sure, okay, yeah, it does. Right. Okay.
Do you have any examples where like epsilon bias space is not part of a specific example?
You mean
No, but
epsilon
I
bias
mean.
spaces in general don't work,
But nice examples, no. So the example I construct will be epsilon biased,
I mean,
but nice examples, right? Classical construction.
Yes, the question is what are you trying to fool? Like say, to solve the fact of the mean entropy
So so we've kind of convinced ourselves that small bias spaces don't fool depth 2 circuits in general, but it turns out that if you stare at the example nicely, I mean in a certain nice way, it turns out that they do fool a nice subclass. And what we're going to show is that so we can fool a nice subclass using epsilon bias spaces, and general circuits can be reduced to this nice subclass, and that's how we're going to go about it. So what's this nice subclass that they're going to fool? So let me tell you about that. So let me say I have, let f be some arbitrary depth 2 read once circuit. Right. So it turns out that the hardest case again is when f has a parity gate on top. So f can be written as and here for each I, yi is a monomial, by which I mean that it's an AND of literals over some set Si of variables. True, but it will help me to consider literals here because right. So yeah, so let me consider literals. You're right in that the distribution doesn't really change if you consider, right. So yi is a monomial over some set Si of variables, and the read once condition essentially implies that Si intersection Sj is empty for all I not equal to j. So I thought there was something else I wanted to say about this. Right. Yeah. So I'm going to make a basic assumption that's not very hard to justify, but it will simplify the proof in this case. I'm going to assume that for each I, that no monomial has very large degree. I'm going to assume that they're all of size at most log n or so. So this is not hard to justify because there can be at most n monomials overall. This is the read once thing. This is a read once polynomial, and if a monomial has degree significantly larger than log n, it's hardly ever going to take the value 1 or. Okay, so we can drop all such monomials without changing the output distribution of our function too much.
So order log n.
Right, order log n. Yeah. Okay, so order log n. Okay. So so now let me define the weight of my function f to be the expected number of monomials satisfied by a random assignment. Okay. So here's a fairly simple observation. So these things are all disjoint. So here's where read once really helps us. When you have a read once circuit, the distribution, the output distribution of the circuit is very, very easy to determine. These are all independent random variables, and we're taking their parities. So as the weight increases, the function gets more and more unbiased. So more generally, the bias of f, which is just the expectation of f on a random input, this is just the product of the biases, expectation yi on a random input. And this thing is just, so what's the expectation of a single random of the monomial yi? Well, this is going to take the value 1 with probability. Recall that we are working on the -1 1 basis. So this is going to take value 1 with probability 1 minus 1 over 2 to the cardinality si, and -1 with probability this thing. So this bias looks like which is it's something that's exponentially small in the expected number of monomials that are satisfied. Right. So this is
So this in turn shows you that you can assume that each of them is at most log n.
No.
If any of them is larger than log n, then it's already very small, right?
No, the bias is not very small. The bias is very large if if one of them is larger than log n, right? So if one of them is larger, if SI is larger than log n, this thing is almost 1. So that's kind of why you can omit it really. If the bias is almost, I don't know, it's like 1 minus 1 over n square, then you can omit all such terms entirely, and this product really doesn't change by much because they're close to 1. Okay. Yeah. So we have this fairly simple observation that says that when you have a large weight circuit, you really have very, very low bias. So large weight implies low bias, and so in a sense this means that the function, intuitively the function f is not very complicated, because in a sense its distribution is completely determined, because when the function has large weight, we know exactly what the function is doing on a random input. It's outputting essentially an unbiased bit. So large weight implies low bias, and note that this kind of covers the example above. The inner product function definitely has large weight. On a random input, you expect to satisfy something like n over 4 variables, so it's exponentially close to being unbiased. Okay. So intuitively, the complicated case is when you have small weight. Yeah. So in this case, you can have maybe, I don't know, a complicated distribution. The output distribution is not as determined as in the And what we are going to show is that the small weight case is actually handled by epsilon bias spaces. Right. So in some sense, the complicated distribution is not really an issue at all. We can handle that using epsilon bias spaces.
The intuition for that?
I'll just get to that in a minute. And the large weight case, well, the large weight case is, well, we already know what the large weight case is going to do. It's going to be low bias. So we're going to ensure that even under distribution, the function is going to output essentially an unbiased bit. So the way we are going to do it is that we're going to start off with a function that has large weight. We're going to restrict it so that its weight becomes small but not too small. Right? So that it's small but not too small. So it's still kind of unbiased. And then we're going to use an epsilon bias space again. So that's going to be a strategy for the two cases. So let me describe each of these in turn. High bias and right, but there the dichotomy is just based on the bias, whereas here is based on weight. So here it's much more transparent. So this kind of thing shows up very often in general. So I've seen it in work on modular sums, on Raghu and David's thing on combinatorial shapes, right? Or rectangles, right? So they, yeah, when you have things like read-one structures where you naturally have a notion of weight, and when the weight becomes large, the distribution becomes simple. Right, even in hour and well, hour and hour.
Like they do this based on the number of the sizes of the test cells.
True, right, but yeah, so but there any non-zero weight implies zero bias. So yeah, I'm not really.
I mean, the generator uses different sizes.
Right, exactly, right. It does. You're right. Yeah. Okay. So,
So for large weight, I mean, can you like do the hour thing?
oh, so what we're going to do is going to be very parallel to what Naur and Naur does, especially in this case.
For the large weight.
Yeah. Okay. So right. So yeah. So the first thing we want to show is that here's the claim. So informally, all small weight functions are fooled by small bias spaces. Right. So more formally, we have to make a dichotomy based on some actual numbers. So if the weight of the function is, let's say, order log 1 over epsilon, this is what we'll mean by small weight, then f is epsilon fooled by any delta bias space where delta is not too small. Okay.
That's already something
Oh, oh, why?
and so the seed length is
Is log n times log 1.
log. Oh,
Oh, I put in at times. Oh, yeah.
you don't know how to get plus.
No, don't know how to get plus.
Because then it's not quite like Nissan.
Oh, so even well,
You get log n over epsilon.
but I mean, you raise it to the power d, so I mean, there is a product. Or
D equals 2, you don't.
But order D.
yeah, but right. So, but I mean, you for d equals 2, you get log n over epsilon to the 6 or 7 or something.
If it does 2, you don't know how to do log n plus.
Right. Yeah. So that right. Okay. Right. So so let me give some intuition for why this is true. So as Ankur was saying, so why would you expect a statement like this to be true? Well, let's consider a kind of extreme case. So we are here in this claim, we are actually considering the case when the weight is allowed to be as large as log 1 over epsilon. But let's instead consider the case when the weight is really, really small. Let's say much smaller than 1. Right. So here's an extreme case. Let's say the weight is much, much smaller than 1. So what does that mean? That means that the expected number of terms satisfied on a random assignment is smaller than 1. Right. It's much smaller than 1. So in particular, the probability that 2 or more terms are satisfied by a random assignment is like a second order term. It's almost negligible. So you might as well assume that on a random assignment either 0 terms are satisfied or 1 term is satisfied. But in this setting, parity and OR are really the same, right? Because parity equals OR on such thing. Right. So for functions where the weight is really, really small, parity and OR are not all that different. And we know that epsilon bias spaces do fool AC0 and in particular DNF. So if the parity gate was replaced by an OR gate, we know that epsilon bias spaces work. Right. So in particular, when the weight is really, really small, parity looks like OR, so epsilon bias spaces work. So in general, when the weight is allowed to be a little large, well, you can't make this argument anymore, but you can still say that the same technique that works for AC0 kind of should work in this case. You can make it.
You can write this as a circuit of this size with just ends and on, and you approximate very well.
Right.
So is the intuition that when weight is larger than 1, but it's let's say 5, right?
Right.
That you're simulating let's say parity on 5 gates with a and/or circuit of some.
Right, you could go that way, or you could just say that okay, start with AC. Look at the proof technique. Look at the proof that shows that epsilon bias spaces fool AC0. That involves the construction of certain kinds of polynomials, and that construction of polynomials goes through in this setting as well, and that's what we'll do.
But does that these others now we said also work as a proof? I mean, you just replace the top gate with the circuit, a threshold circuit.
Right, but that will be an approximation. You will need an upper approximation and a lower approximation, and then you will have to, right? I mean, you can't just get an approximation, right? So, right, does that make sense? Yeah, you need sandwiching or something, just something that's an approximation.
Polynomials just in the language of circuits. The circuit operation.
Right, you could probably upper and lower sandwich by circuits and then do it, but in either case, maybe some sort of sandwiching is necessary.
Are you sure? Yeah. I mean, can't you just write? Suppose that two of them are satisfied, so you just write the row of ends of pairs.
Right.
And let's say it's a good enough approximation.
But you'll have to approximate it not just to 2, but up to I don't know some sort of error, right? I mean,
So the issue is
to log 1 over epsilon or something.
Sandwiching circuit becomes as a function of.
Sure. It's going to be something like exponential in log 1 over epsilon, and maybe which is fine. But right, so maybe what you're saying will go through, but I'm not entirely right. The approximation needs to be good under a small bias space as well. So yeah, it should not just be an approximation under the uniform distribution. So if you don't care about that, then you have to construct sandwiching.
But that will be true, right? Because in the approximation, you're only
Right, right. And so what I'm saying will also go through for a very, very similar reason. Okay. All right. Okay, so let's prove this claim. So how are we going to prove this claim? We are going to prove it using the technique of sandwiching polynomials. Okay. So let me just recall the kinds of polynomials we need in order to show that epsilon bias spaces fool our function. So what we are going to do is we are going to construct polynomials p upper and p lower. Polynomials over the input variables. So these are polynomials over the reals, just to be clear, such that, well, for all x, these guys sandwich the function f, and furthermore they sandwich it reasonably well. So the error in these approximations is not too large. The easiest way to say it is, let's say, and finally that these polynomials are reasonably well behaved. So if I look at the L1 norm of these polynomials, so the L1 norm is just the sum of the absolute values of the coefficients. So if I have this result, this straight away implies that any small bias space, any delta bias space, epsilon fools f with error that's at most the error here, the epsilon by 2 error, plus something that comes from the L1 norm. Okay. So in particular, if I set delta to be something like epsilon over L, then I'm in good shape. This entire any delta bias space, epsilon fools f. Oh, sorry, fools f. And so it turns out to be fairly simple to construct sandwiching polynomials for these things. So sandwiching polynomials, I should mention, have a fairly rich, though somewhat recent history. So starting with the work of Badzi and Razborov and others, we have sandwiching polynomials for AC0. But in the context of read-once functions, these things are actually fairly easy to come by. So what I'm going to talk about really follows a result of Clivens, Lee, and Wan, who constructed such sandwiching polynomials in the context of read-once DNFs. Okay. So what are we going to do? Well, we have this function f, which is a parity of a bunch of monomials, and let's write it out exactly as a polynomial. So let me write it. So well, it's a product of because I'm working on the -1, 1 basis. So, but it's going to be helpful for the purposes of this particular construction to work in the 0, 1 basis for just the yi's. So it's a product of where yi tilde is the 0, 1 version of yi. Okay, so yi tilde is just and so from here the construction of sandwiching polynomial is very, very transparent. So you just expand out and truncate the expansion at various degrees. So so f of x is, well, if I expand out, what I get is something like sum over I minus 2 to the I times the elementary symmetric polynomial in the y's and my upper and lower sandwiching polynomials are just going to be truncations of this expression. So the upper approximation is just going to be I equals 1 to I equals 0 to d 2 to the I. Right. And sure, they're increasing. So it depends on the parameter that I choose. Oh, I see what you mean. So let's see. So here I choose d to be something. So what do I need to choose d to be? I choose d to be odd, I guess. Oh, d needs to be even. Right, you're right. If I choose d to be even.
No, he's asking why is the tail small.
No, he's not asking why the tail is small. He's asking why is it increasing beyond a certain point, right? So why does it say above the function, right? Well, yeah, it's just the standard inclusion exclusion formula. So.
But for an alternating series, if the terms are decreasing, then I know that.
Isn't it called like the Bonferroni?
Right. It's just that yeah, the alternate terms actually sandwich your thing, right? You don't need it to be increasing or decreasing. In the standard inclusion exclusion formula, it always holds. It holds even at the first level, though the approximation might be very, very bad and the terms might not be small, right? So if you have a bunch of terms that occur with probability half, then I don't know, the union bound is still true, right? So I mean, it's like the union bound is still true irrespective.
Some 1 minus 2 plus 3 minus 4 up to some, and then if you stop at an even term, it's not an upper bound.
Oh,
This
it
is
always.
only true for the things generated from an inclusion exclusion.
Right.
That's yeah. I mean, it's
Right, but there's
Bonferroni.
a 2 to the I. That's still.
Yeah, there is a truth. Yeah. So that makes it okay.
Now I thought it only applied when it was product 1 minus pi, where pi is between 0 and 1. But now your pi is no longer between 0 and 1.
No, well, it even applies to arbitrary numbers, right? I mean, you're talking about unions of sets and so on. I mean, oh no, I don't know.
I think
No, so it's
like
apply.
weighted union, like
So what
Right.
I mean, what if you look at the expectation instead is like you look at it, the probability that it's 1 and the probability it's minus 1, subtract it. So if you truncate it at some bound, then do you agree about the sandwiching?
So pi minus 1 minus pi, and you look at the product of such terms, and then you look it up.
And so nevertheless, it's actually fairly easy to argue that it does hold. So yeah.
And the general fact is, whenever you have product 1 minus 2 yi, where yi's are arbitrary real numbers.
So I know it for no. So what am I saying? I'm just saying this for 0, 1 yi's. For 0, 1 yi's, this definitely holds. That's all that's the only claim I'm making, and that's the only thing I need to make even, right? Because when I plug in, I only need this to hold for inputs x coming from the hypercube. So then yi's are always 0 or 1, and then this always holds.
So this formula is Bonferroni. The way I know it, if the 2 was not there, the 2 to the I was not there.
Well, that's for or whatever. This is for parity. I mean, so the 2 is necessary for the parity thing.
Right.
Yeah. So that's because of the Okay. So yeah. Okay. So it's kind of fairly easy to check that these are both sandwiching polynomials. That one is a lower approximation, the other is an upper approximation. What we do need to do is analyze the error of these approximations. So okay. So let's just analyze the error. It turns out it's not very difficult. It's a fairly standard calculation. So if I look at the difference between the lower and upper polynomial, this is precisely the symmetric polynomial of degree d plus 1 in the yi's. Right. So let me just analyze exactly what the term is. So this is the sum over all s of cardinality d plus 1. Okay. So so let me just say that the expectation of this thing, well, it's 1 over 2 to the cardinality si, but let me denote it by pi. So here pi and the standard way to bound this is using just the AMGM inequality.
Now there is a 2 to the D.
Oh, good. Oh, yeah, thanks. Right, there is. Yeah. Yeah, thank you. Yeah, so this thing is at most. So just using the AMGM inequality, this thing is at most n choose d plus 1, 2 to the d plus 1, some pi, not n choose d plus 1, t choose d plus 1. T is the total number of these guys. So yeah, it's y1 to yt. Okay. So just upper bounding this in a standard way gives us something like order. The sum of the pi's is just the weight of the function, right? And the weight we are assuming is at most log 1 over epsilon. So it's order log 1 over epsilon by d plus 1 whole to the d plus 1. Right? So set d to be something like a large enough constant times log 1 over epsilon, and this thing is going to be less than epsilon by 2.
D is somewhat of the first degree of assembly or that, but now it's just the value of quantity. It has nothing to do with that.
Right. Yeah.
What's the degree of polar?
It's the degree of these lower and upper approximations. Right. Okay. Good. So right. So we've constructed lower and upper approximations that are reasonably good. We just need to analyze their L1 norm. It turns out there are also low degree approximations, but the L1 norm is fairly easy to analyze. So let's just do it. Okay.
So where does the t choose d plus 1 come into the upper bound?
Right. So you just upper approximate this using Stirling. So it's et by d plus 1 to the d plus 1, but the t goes away.
Oh, okay. Yep. Okay.
Yeah. So okay. So now let's just analyze the L1 norm of these two things, and we are essentially done. So what's the L1 norm of these two quantities? Well, the L1 norm of the upper approximation or the lower approximation either is at most, well, it's a, let me just do a lower approximation because it has more terms. Let me just use the triangle inequality and do something brute force. So I have d plus 1 terms, each one has a coefficient that's at most 2 to the d plus 1, and let me just look at the maximum L1 norm of any elementary symmetric polynomial. Now each elementary symmetric polynomial is the ith elementary symmetric polynomial is made up of n choose I terms. Each term is a product of these yi tildes. So these yi tildes are ands of some literals. So products of yi tildes are again ands, and ands have constant L1 norm. Right. So the L1 norm of this thing is essentially the number of, is at most the number of terms that appear in it. So that looks like n choose d plus 1 more or less. So let me just do a very bad bound, something like n to the order d. Yeah. And recall that we said d to be some order log 1 over epsilon. So this is like n to the order log 1 over epsilon. Okay. Yeah. So with these parameters, all these things check out. So the L1 norm is like n to the order log 1 over epsilon. Then, and these are fairly good approximations. So this means that if we set delta to be roughly 1 over the L1, epsilon over the L1 norm, which looks like 1 over n to the order log 1 over epsilon, we are done. Right. Okay. So yeah. So all of this is exactly the proof that goes through for DNFs. All we have done is that seen that the construction of sandwiching polynomials actually yields a little more than just what it yields for ORs. It actually works for parities up to a certain level. Okay.
What is the equivalent step of this for standardized? You'll talk about it later?
Right. I'll get to it later. Yeah, but right. So yeah. So this handles the case when we have a depth 2 circuit, but it has low weight. Yeah. So now we just need to handle the large weight case. And recall that our intuition is that the large weight case is kind of uncomplicated because we know what the function behaves like on a random input now. We know that it's unbiased. Okay. So yeah. So let's do the large weight case. we leave this one. So yeah, so I won't need these anymore. So in this case, so we're going to assume that the weight of the function now is some large constant, maybe some constant c times log 1 over epsilon. So this in particular, this means that the bias of this function, which we call is just the expectation of the function, is at most something that's exponentially small in the weight, which is say at most epsilon square. So it's really, really small. So what we need to do is now ensure that under our pseudorandom distribution, whatever it may be, so let's say y is chosen as an input to our generator, the one we define, that this continues to hold in that case. So f of g of y, let me write it as an expectation, f of g of y is also considerably smaller than epsilon. This is what we need to ensure. So in this particular case, so note that if our weight was actually not, it's at least c log 1 over epsilon, but if we knew that it was c log 1 over epsilon, then we could still get away with the application of epsilon bias spaces. The problem here is that the weight might be much, much larger, like in the inner product function, where the weight is something like n, right? So what we have to do is, when the weight is really large, what we want to do is kind of restrict the function and bring its weight down to roughly c log 1 over epsilon, and then we'll just apply an epsilon bias space and we'll be done. Okay. Right. So we're not going to hash. We're going to restrict. Yeah, we'll restrict, but with a pseudorandom restriction. Right. So what we're going to do is apply a technique that's been very useful in proving lower bounds and in constructing pseudorandom generators. And this is a technique that Parikshit also spoke about a few weeks ago. So what we're going to do is apply a restriction. So what's a restriction? So a restriction for us is simply a function that maps the input variables x1 through xn to 0, 1, or star. So variable being set to 0 or 1 means we're setting it to that Boolean value. Being mapped to star just means that we're leaving it alone, right? And we are going to be looking at random restrictions. Right. So we're going to fix some probability q 0, 1, and we're going to look at restrictions which are sampled from the distribution RQ, which means that every variable xi is set to star with probability q, so it's left alive with probability q, and with probability 1 minus q by 2 it's set to 0 or 1. Okay. So our hope is, so note what we are doing with the restriction is that we are getting rid of some of the variables, and it's natural to assume that if we get rid of all the variables and the function has 0 weight, so it's natural to assume that if we choose our restriction probability q just right, the weight will reduce to an extent that the function still be unbiased, but only to an extent that we can actually fool it with epsilon bias spaces or small bias spaces, right? So that's the hope. So let's just note a few silly things. Q equals 0 means that we are not setting anything. So this just means that we are leaving the function alone, right? So this means that the restricted function f rho is just f. And in particular, if I look at the weight of f rho, this is always going to be like the weight of f, which we are assuming is fairly large. On the other hand, if I set if q equals 1, that means I am setting every bit, every input bit. This means that f rho is always going to be some sort of constant. Yeah, in this case I think of with the weight of f rho as being 0, right. So as far as I am concerned, constant monomials don't contribute to the weight. The only monomials that contribute to the weight are things that, well, that are alive, that have a chance of being both 0 and 1. Okay. So somewhere in the middle I'd like to find a middle ground between these two things, where the weight, well, it's large at 0 and small at 1. Oh, oops, have I flipped things here? Actually q equals 1 is the case when the function is, the function is just left alone, and q equals 0 is the case when every variable is set. Right. So so I'd like to find some sort of middle ground for q when the weight of the restricted function looks something like c log 1 over epsilon. That means that it's still unbiased, and therefore I can fool it with small space. Right. So to that effect, let me define this kind of simple function. So this is a function that maps q to a real number. So this is just maps q to simply right. So let's just calculate this function brute force. It's not very difficult. Okay. So what is wf of q at an arbitrary q? Well, wf of q is, well, it's this quantity, and the weight of this, just the way it's been defined, it's the sum of the weights of the restricted functions yi. Thanks. Right. And so what is it for a single monomial yi? Well, for a single monomial, it kind of looks like this. So well, if I take a monomial and restrict some of its variables, if I set let's say the monomial is the product of variables and not negated literals, there are no negated literals. If I set any of the variables occurring in the monomial to 0, then the monomial disappears. If I set all the variables in the monomial, then again the monomial is now a constant, and therefore it does not contribute to the weight. So the only way it can contribute to the weight is if some of the variables are left alive and the others are set to 1. Right. So in general, this is going to be like the sum over the number of variables that are left alive. Let's say that can be some number between 1 and cardinality si. Well, I can choose the set of variables that are left alive, and then I'll get some weird binomial, right? So it's the variables are left alive with probability q. The remaining all have to be set to 1. So that happens with probability 1 minus q by 2, right? And in this case, the monomial actually contributes weight 1 over 2 to the j. That's one final one. Right. So this kind of simplifies very nicely. I can take the powers of 2 out. All the powers of 2 add up to n. So I can take the powers of 2 out, and this is essentially a binomial with a single term missing. Yeah. So this is it's not 102 to the m, 102 to the cardinality si. Okay. So that's what the expected weight of a single monomial is. Okay. So so you plug it in and you get some ugly expression for the weight of the entire thing. But we're not going to need too many things about this. So what we're going to need are the following fairly simple observations. Let me make it up here. Okay. Right. So first of all, I need to establish that there is such a Q. So let's just do it. It's kind of simple. So let's. Right. So Okay, so let's just look at this function, right? So it's clear that this thing is kind of monotone in Q, right? And the second thing that's kind of not too hard to see, but is useful for us is that so though this drops as Q drops, it doesn't drop too quickly, right? So how fast can this function actually fall? Well, this function falls quickest when Q is very close to 0. But when Q is very close to 0, this is roughly linear. Okay. So this really looks like this, yeah, for any Q. So it drops, but it doesn't drop too quickly. Right? And what we know is already is that this thing is large at 1, it's large. And it's not too hard to see that if I set my star probability, the probability Q to be something like 1 over n, then it's kind of small, because the expected number of variables that survive is only 1. And then, right? So, well, it's large at 1, it's small at 1 over n, and it's not dropping too quickly, though it is dropping. So there must be some point where it's just right. So therefore, there exists Q. In fact, I can choose Q to be a power of 2 for I in say log n, such that, well, it might not be exactly what I want, but it's going to be close. Okay. So makes sense. So that means
And then to this new thing you can apply.
absolutely. So right. So if I do this entire thing by setting my random first restricting the function with star probability Q, leaving every variable alive with probability Q, then the expected weight of the restricted function looks something like C log 1 over epsilon. And what's more, this is going to happen with high probability, right? This is just a sum of independent random variables, right? So then, in fact, if rho is chosen from RQ, then with high probability, you actually do have this, maybe with slightly more slack. So maybe, I don't know, C by 4. Right. And once you are there, so once you've restricted the function, then you can actually apply the construction for the low weight case and you'll be done. Right. So suppose somebody came and told you, here's this I, you know this function, here's a function, I'm going to give you a function such that Q equals 2 to the I is good for that function, in the sense that when the function is restricted with that particular kind of random restriction, the weight falls into the right range. Then I can design a pseudorandom generator fairly simply, because what I'm going to do is restrict the function using this particular family of random restrictions, and on the remaining variables set them according to a small bias space, where that small is really determined by that claim. Right. Exactly. Good. Great. So right. So exactly. So right. So what Avi is saying is that of course the problem with this strategy is that you're using a lot of bits to choose your random restriction to begin with, but you don't really need all that many random bits. If you look at this particular analysis, well, all it uses is that well, it's analyzing the weights of monomials at a time, and each monomial, recall, is of size at most log n. So if a random restriction was chosen not completely independently, but using something like a log n wise independent distribution, then this same analysis would still go through. Almost log n would also go through. That would be fine. Right. Good. Right. So, but we also need to say that this happens with high probability, and for that we used a Chernoff bound to begin with. But in order to apply it in the setting of pseudo-random restrictions, we cannot apply Chernoff bounds, but we can apply high moment inequalities, right? So if you use something like a no, just k-wise independent bound, right? So we'll do this with if I do it with log n log 1 over epsilon wise independence. So if rho is chosen with log n log 1 over epsilon wise independence, then every set of at most log 1 over epsilon monomials is roughly independent, and therefore I can apply the log 1 over epsilonth moment bound, and it turns out that that is enough for all these purposes. Okay. So let's just see that that gives us some sort of pseudorandom generator. So the pseudorandom generator is essentially defined like this. So it's a, remember, it's a pseudorandom generator that depends on I, because we know I to begin with. It takes some seed, let me not call it Si, let me call it Ti, not Ti, Ri, to minus 1, 1 to the n, right. So what does G do? Well, it uses its random bits to first sample rho, but from a log n times log 1 over epsilon wise independent distribution, and then it sets the bits that are not set by rho, it sets the remaining bits by using a delta bias space, a random sample from a delta bias space, where delta is as in the claim. So delta equals 1 over. Yeah. Okay. So yeah. So the seed length of this, it's fairly easy to check, is that okay. So this is the dominant term in this entire expression, and the seed length of this is, it looks roughly like log squared n log 1 over epsilon. So let me just write that down here. Oh. Sure, you're right. You can save a log. So right. So the seed length of Gi is roughly like log squared n. Okay. And so now, okay. So the problem with, of course, this construction is that we don't know I to begin with. So what we are going to do is, well, we are going to guess I. So the final generator for the depth 2 case looks something like this. So the seed to this thing is going to be, so we've already constructed pseudorandom generators for every I in 1 to log n, G1 to G log n. We also have a pseudorandom generator that works in the low weight case. Let me just call that G0. So what we're going to do is combine it in any one of many possible ways. So we're going to use a way that Avi and Russell used in their paper. So the seed to G is going to be just a bunch of seeds to each of these guys. So Z0, Z1, Z log n, and we just output the parity of these things. Okay. So now why does this entire thing work? Well, let's suppose that we are actually dealing with a low weight function. To analyze a low weight function on the output of this generator, what you would do is you would fix Z1 through Z log n, right? And when you fix Z1 through Z log n, the output of this generator really looks like the output of, so let's say f is low weight, then fix Z1 through Z log n. In that case, the output of the generator really looks like the output of G0 on a random input plus some fixed thing, right. So really applying f on this random input is like applying, so f of this thing is really applying this random input to the function that kind of takes its input, XORs a to it, and then applies f, right. So this is like, so I've taken this read once polynomial and I've kind of XORed it. I've XORed each, I mean, I've negated some of its input bits and then I'm applying it. That's still a read. Right, that's why it was convenient to keep the literals. So I still have a read once polynomial, and more importantly, it's still a low weight thing because the weight is completely determined by a combinatorial structure of the size of the monomials. So therefore, this thing is fooled, and therefore we are done.
Oh, so this class is closed under translation.
This class is closed under translations. So in general, if I wanted to work with weight, if I were working with a function f such that q equals 2 to the 1 over 2 to the I is good for f, if I XORed the function by any fixed a, 1 over 2 to the I would continue to be good for f, and hence this entire construction would work. Okay. Okay. So that concludes the depth 2 case more or less. So there's only half an hour to go. So we could take a break now, or I can just go ahead and finish it because it's not going to be much longer. I'm not going to get into too many technical details in the remaining. Okay. Okay. So how do we extend this analysis to depth d? It turns out that things are not very different. So it's now depth d read once. And let's assume for now that we have pseudorandom generators for all smaller depths, right? So we have now our depth d function is really looks like the XOR of a bunch of depth d minus 1 circuits, right? Yeah. Good. So it's a good. Let's do that actually. Let's start with AND, right? So okay, f is a depth d read one circuit. The top gate could be an AND or an XOR. Let's just see that AND actually reduces to XOR fairly easily. Okay. So the first thing I'm going to assume is that f is made up of alternating layers. So let me just actually delete this. I don't need this anymore. So I can ensure beforehand that my circuit is made up of alternating layers of AND and parity gates. You can always kind of change the circuit a little bit, increase its depth maybe by a factor of 2, and ensure that this happens. Okay. So now, well, the top gate of the output gate of f could be an AND or a parity gate. Let's look at the case when it's an AND gate. So f is right, and these guys have parity gates as their output gates. So what do we do in this case? Well, it turns out that it's kind of easy to see that the AND of x1 to xt is a low L1 norm function. So it can be written as a low over the reals. It can be written as a low weight combination S subset of t of the parities of the right. So it can be written as a low weight combination of the parities. So what do I mean by low weight here? That most well it's some order 1. Okay. So if I can fool all the parities, then I can fool these guys. But the parities of FIs are just depth d minus 1 circuits. So by assumption I can fool all these guys. So I can fool these guys as well. Okay. Right. So the AND gate on top is never really an issue because it always reduces to the parity gate. Okay. So the only interesting case really is when the top gate is a parity gate. So let's say now that f is no, it's just 2. Okay. So right. So the parity case. Okay. And so in this case we proceed in a way that's very similar to the depth 2 case. Only we need to handle things slightly differently. So the weight of f, this time we define to be, well, this was the right definition actually in the depth 2 case as well. The sum of the variances of the FIs. Okay. It just turns out that in the case of AND, the variance is roughly determined by the probability that FI is 1. So it worked out. And what's again easy to see is, well, essentially what we said there. So the bias of f is something that's exponentially small in the weight of f. Okay. This turns out to be a similarly trivial claim. Okay. So we are again left with the kind of dichotomy that we had in the depth 2 case. We have a large weight case and a small weight case. Right? The large weight case seems to us to be simple because again the output of the function is determined in some sense. The small weight case seems to be complicated, but things work out for precisely the same reason. Okay. So what happens in this case?
I mean, again, using sandwiching polynomials? Or
Right, but the sandwiching polynomials, right. So what we are going to say is that all small weight functions are not fooled by small bias spaces, but fooled by generators that fool lower depth circuits by PRGs for smaller depths.
Is there a counterexample to using epsilon? I mean, using the original like epsilon bias spaces in this higher depth case? Does it not work? Or?
Sorry. Right. Yeah. I mean, you can't just use, but a small weight. No, I don't understand.
Weight,
yeah.
Small weight in depth 3 is justified. So if you have counterexamples for depth 2,
It's possible. Right. Makes sense.
So, but you don't lose it the parameters when you say just. So,
Right.
Yeah, which is the seed length of this.
Absolutely.
Smaller than.
Right. So any so here's the formal statement. If the weight of the function is order log 1 over epsilon, then f is epsilon fooled by any PRG for depth d minus 1 with error delta, where delta is again as before 1 over n to d. So you just you need to lose in the error, and that's okay. And the proof of this is verbatim what I did in the F2 case. The only thing was there I actually got polynomials. Here I'll be looking at a polynomial in the FIs. Right. So I don't have that anymore. Okay. Oh, I do actually. No, I don't. Okay, I don't. So right. So what we did in the depth 2 case is that we sandwiched f by polynomials in the yi's, which turned out to be polynomials in the input variables. What we are going to do in this, what's going to happen in this case is that f is sandwiched by polynomials in the 0, 1 versions of these FIs, just as in that case, right? But terms in this polynomial are just products of these things, just ands of these things, because we are working in the 0, 1 world. But these are already circuits whose output gates are ands, so ands of ands are ands. So these are really depth d minus 1 circuits, right? So f is going to be sandwiched by polynomials in these guys. So it's essentially going to be sandwiched by a low weight linear combination of lower depth circuits, right? And hence anything that fools lower depth circuits with small enough error is going to fool f. Yeah. So everything goes through exactly as before. Yeah. So what's interesting is the higher depth case. Sorry? Oh, the higher weight, right? The higher weight case. So let's assume that the weight of f is some large constant times log 1 over epsilon. Again, now the bias of f is determined, and we need to ensure this. Right? So again, we are going to use random restrictions, but this quantity, which was so simple to analyze in the AND case, well, it's not immediately clear that it can be analyzed in the higher depth case. Because I mean the weight is not a trivially determined quantity. It seems to be a complicated expression. However, it turns out that we didn't really use too much about this exact formulation. All we used was the fact that this function is monotone, it doesn't drop too quickly, and it turns out that we can get some sort of expression for this quantity for an arbitrary function, and that expression also turns out to have the same properties. So let me just tell you what that the expression for an arbitrary function. Right, for any Boolean function, it turns out it's essentially related to the noise sensitivity of f. Yeah. So, okay, so let me tell you what. Right, so again, this is the quantity we want to estimate, and in this case this turns out to be the sum over I equals 1 to t right. So we are taking this Boolean function fi, we are restricting it.
Just intuitively, the noise sensitivity of f is going to govern how well it's approximated by a low degree.
Right.
With the low degree expansion, and then it's the high degree terms that really govern the fact that when you do the restrictions, it'll drop very rapidly.
Right. Exactly. That's exactly right. Yeah.
I mean, the monotonicity will trivially.
Absolutely.
Or even more directly, because f is not biased, it's exactly the noise.
This is exactly the noise sensitivity. In fact, there's an exact equivalent. So good. So let's just see that that's the case. So recall that. So what is this quantity? Well, we are picking a row that that leaves every variable alive with probability q, right? And we are looking at the variance of the restricted thing. So recall that that's just up to constant factors. This is just I pick two inputs x and y, and I'm looking at the probability that fi of x is not equal to fi of y. So it's really the expectation of 1 minus. Let me write it as the probability over x and y. Fi of x is not equal to fi of y. Oops, let me write this. Yeah. So fi rho. Sorry, is this what you were saying? Okay, thanks. So what is this? Well, I'm plugging in, so putting these two, the restriction and the inputs together, I'm picking two kind of correlated inputs x1 and y1, and I'm looking at the probability that fi of x1 equals fi of y1 is not equal to fi of y1, right? So what relation? I'm putting the restriction and the inputs x and y together. So here I'm plugging in x and y for the bits that are left alive by the restriction. Right. That's for the entire function. I'm analyzing a single term of this. Right. Just a single term. Right. So what relation do x1 and y1 bear to each other? Well, if right. So x1. So I'm setting the restricted. I'm evaluating the restricted functions on the inputs x and y. So I'm evaluating the original function on inputs x1 and y1. Say, right. So on a bit that's set by the restriction, x1 and y1 agree. Right. So that's so they agree on, let's say, a 1 minus q fraction. Right. On the remaining bits, they agree with probability q over 2. Right. So this is really I'm choosing x. Let me not call them x1 and y1 because I want indices. Let me call them x prime and y prime. So I'm choosing x prime and y prime so that x prime I equals y prime I with probability, well, 1 minus q plus q over 2. So 1 minus q over 2, right? And they're not equal with probability q over 2. Right? So essentially I'm picking x and y independently at random, condition of the fact that they are kind of q correlated. Right? And I'm looking at the probability that fi of x prime is not equal to fi of y prime. And this is precisely like the noise sensitivity of f with parameter q or q by 2 or whatever you choose to call it. So this is like the noise sensitivity of fi. Yeah. So I might have lost some constant factor somewhere. Okay. Right. But actually, okay. So this fact is not really important. It's just that we have there's a clean expression for this in terms of the Fourier spectrum of f. So this is the sum over all s not equal to 0, non-empty, fi hat s squared 1 minus yeah. So we have a term which is essentially exactly very similar to the term that we had before. It looks almost exactly the same, and for the same reasons this function is monotone. It doesn't drop too quickly, and of course at 1 it's large and at 1 by n it's small. So So precisely the same argument says that if I choose a random restriction with star probability q for some nice q, then the weight of the function is going to lie in the right range. The expected weight of the function is going to lie in the right range, right? And yeah, this is the expected weight. Okay, and if rho is actually picked from RQ, then with high probability, I should have said, the weight of the restricted function is in the right range, right? Okay, right. So it seems like we are more or less done. The only thing is that we need to choose the random restrictions. Sorry. So
You didn't assume anything about Fi at all.
I haven't assumed anything. I'm going to assume something about Fi now. Right. So we need to choose. Of course, now the point here is that we are still choosing the random restrictions independently at random, and then this entire strategy works. But we need to choose the random restrictions in a kind of pseudo-random way in order to actually construct a pseudo-random generator. And that's where the actual character of the FIs, the fact that FIs are computed by depth d minus 1. Right. So now we cannot no longer use the trick that we used before, because there we could assume that every monomial depended on a small number of variables. So all these terms were small. So and then we could make the entire thing go through with just log n wise independence more or less. We can no longer assume that because these are arbitrary circuits. Right. So right.
I mean, you can still just development
The parity gets in depth d minus 1. Yeah, yeah. If it was just AC0 circuits, I could probably have used Brewerman's result. That's true, right? But okay, but so we just need to get around this final fact, right? So there's just okay. So I no longer need the small values. Okay, good. So okay, so here's the only challenge really that we need to overcome. So we need to choose this row pseudo randomly, right? So that, well, what we would like is that with high probability the weight of f after applying the random restriction lies in a reasonable range. Right? Yeah. And so the idea is to do it similar to what we did in the dep2 case, where we first ensured that the expectation lay in the right range, and then that the higher moments were small, and therefore we could argue using a moment bound. So first thing is to ensure that the expected weight of this quantity actually lies in the right range. So the first thing, so what we'll do is we are going to choose rho pseudo randomly, and we are going to ensure that the weight of f rho, which is like the sum of the variances fi, is in a reasonable range. Right. So I'll show you how to do this. The moment bound, it follows similarly. I have not yet said how to do this. Yeah, have to do. Right. So that's going to be the idea. We have to choose rho in a way that fools depth d minus 1 circuits. But that's, yeah. So we'll see that that's not quite enough. So we'll see. At least I don't know if that's quite enough. Okay. So how are we going to choose rho? Right. So know that rho is made up of two independent parts. They're the set of variables you choose to leave alive, and the variables that you choose to set the way you set them. Right. So really, I'll think of sampling rho as being two independent parts: sampling a set and sampling a setting to the set bits. So just for simplicity, let's think of this as a 0, 1, I mean an n bit vector, and this also as an n bit vector. Though I really need to only sample settings for the bits I'm actually setting, I'm going to get an n bit vector overall, and then I'm only going to use the bits that I actually set. Okay. Okay. So so now what I'm going to do is, well, I know that if I and z are chosen, that I is chosen so that every bit is say 1 with probability q and 0 with probability 1 minus q, and z is chosen independently at random, then this is true. right? Because this is what I'm assuming. I'm assuming that Q has been chosen so that if rho is chosen completely independently, then this happens. Now I need to choose rho pseudo-randomly, right? So I have to replace. Well, the first thing I'm going to do is I'm going to replace the choice of Z. Right now it's completely uniform. I'm going to replace it by a pseudo-random choice. Then I'm going to replace the choice of I by a pseudo-random choice. Let me show you how to replace the choice of Z by a pseudo-random choice. Okay. Yeah. Okay, I don't know.
In some sense, you need a PRC for depth D-1 is biased input.
No, that's biased inputs are not really so much of an issue.
Okay, and I mean, would that be enough?
So it's not clear. So that's what I'm going to get to. So even in the Z case, you're going to see that there's going to be a slight problem. Okay. The problem is that I have to fool the variance and not the. So variance is like a second moment as opposed to just fooling the function, which is the first moment, right? So now, okay. So what's the quantity we need to fool? Well, we need to fool this quantity. So what we are going to do is ensure that what we have to do is ensure that variance f rho. Let's say rho is the independent distribution. I want this to be roughly like, and let's say this is a pseudo-random distribution. So I want to choose this, and Z prime is chosen pseudo-randomly, and I want both these quantities to be roughly the same.
But it still is one function, even though it's a variance, because these are independent.
Right, but yeah. So, but still, how do I fool the variance? Right, fooling the variance is slightly different from. Yeah, I agree that Fi is the different functions are as of now disjoint, but still there's going to be a small issue that will come. So, right. So what we want to do is preserve each of these terms, term by term. Okay. So how are we going to preserve these terms? Well, what we're going to say is. Yeah. Okay. So let me look at this particular quantity. Okay. So this looks like expectation over I, expectation over Z. The variance, let me just write it out. I pick X and Y, and then we're really looking at Fi rho X. Right. Yeah. So this is just the variance by definition, right? So this is just expectation over I, Z, X, Y, Fi rho of X. Okay. So once more, I'm going to think of X and Y. Though really, I'm only applying the X and Y to the bits that have not been set by rho. I'm going to think of X and Y as really n-bit vectors, n-bit inputs, and I'm only going to use the bits that are inside I. Really. Okay. So what does this look like? So this looks like expectation over X, Y. Let me just take Z inside. Expectation over I, and let me just expand out the square. The squares of these functions are 1, so that's not going to be a term that will hurt us. What's going to be interesting is the other term. So it's 2 Fi. So Fi on this particular input really looks like X right. Okay, so this is, so what I would like to do is choose Z pseudo randomly so that this term is preserved, more or less. Okay. Okay. So okay, so what I would like to say is that if I choose Z in a way that fools depth D-1 circuits, this term is preserved. Well, that looks on the face of it very nice, because well, ignore the fact that this is a parity of two depth D-1 circuits. So I can write the parity as an AND, right? So if I fool and these two are circuits whose top gates are AND. So when I write things nicely out, maybe this will become a depth D-1 circuit and I'll be fine. But the problem here is that this ruins the read one's nature, because both of these circuits are reading the variables inside Z. Okay, So that's the main issue. So the fact that it's a parity is kind of a smoke screen here. The fact that both these are reading Z is a problem. So I don't want to use Cauchy-Schwarz. I want to preserve this term entirely. I don't understand how I would use Cauchy-Schwarz. So I want to choose Z pseudo-randomly so that this term remains exactly the same, maybe with a small error. I need I want to preserve this thing, right? Because I know that this thing is in the right range, so I want this thing to be in the right range. How do I do that? Because I just preserve it term by term. I don't know how else to do it. Yeah, I want the weight to be around the right quantity all the time. Right, so I need to fool this thing, and I don't know how to fool this thing because it reads Z twice. Right. So one way to do it would be to say that, oh, if I could fool dep D minus 1 read twice, then I can fool dep D read once. Yeah. And this will multiply the reads going down level by level. Yeah. So that's one way to do it. That's something we tried for a while. So we haven't really been successful with that way of doing things. But the thing is that this is really much more structured than just read twice. So if I look at these two circuits, they are very, very related to each other. I start with one circuit, which is the circuit for Fi, and I substitute a few of the variables according to these x's and y's. Right? And I'm looking at the circuit on the remaining. Right? So these circuits are very, very parallel to each other. They kind of split variables in a very similar way. They share a lot of combinatorial structure. Yeah? And it turns out that these give us classes of read K circuits that we can fool. So let me tell you then the final result, and so now this kind of motivates the final induction that we go through. So right. So here's the induction step. So the induction statement is that for all D, for all constant depths, for all K, there is an explicit PRG there is a PRG, there is an epsilon PRG, say, that fools well, not one function, but K functions, F1, let me say F1 through Fk, right, with the property that all these functions are obtained from a single function, read once function, by substitutions, such that there exists F in depth D read once, and for all I, Fi is obtained is a projection of F. Right. So it's a projection of F in the sense that Fi is obtained from F by taking a few variables, maybe negating a few, setting a few, and things like that.
But the number of
The same set of variables, absolutely. Oh, no, I mean different sets of variables could be free across different Fis. Yeah, so that property will get ruined through the induction. So yeah, so every Fi is probably it's a function on a subset of the variables where it's obtained from F by projection, in the sense that you leave some variables alone, you negate a few, you set a few others arbitrarily. Right. And for this thing we have a general a PRG with seed length, again similar to what I said earlier, but again with some dependence on K, log n to the order D, log 1 over epsilon to the order 1 times. No, so K will be like 2 to the D, because you start off with a read one circuit, then you double, so you double maybe D times, because every time you reduce depth by 1, so K becomes like 2 to the D. So this gives you the 2 to the D square factor that I was talking about. So no, we don't use Braverman at all. So yeah, we don't really get that loss, right? Yeah, so right. So if we carry this as our induction statement through the entire proof, so again the read once thing can be done in this setting, right? And if we carry this through the entire thing, it turns out that everything works out. And
Fooling a family just means that you get the distribution.
right, you fool them in statistical distance.
And fooling is statistical distance fine because then you can do this exorbitant.
Right. Exactly. That's exactly right. Okay. So and yeah, so this is the statement that actually carries over to the entire thing, and then right at every point this k becomes 2k when you reduce it. Oh, right. So as in, if you want to fool one of these guys, well, if you want to fool all of these guys, then you can XOR it. You can. It's sufficient to fool the XORs, and then you can break things up. So you can use the XOR lemma, and so that's
I mean, if you want to get this
right.
distribution, it's enough to get the exhaust.
Right. Well, it's enough to even get the ANDs. So at certain depths we'll use ANDs. At certain depths we'll use XORs.
Whatever
Right.
is at the top.
Whatever's at the top. Right.